Hi, this is TheoryStation. I'm John Duggan. This program that we're in is rational choice modeling. The current series is the Basic Formal Theory Toolkit, and we are in installment 18, I believe, of the series. So we are still talking about the one-dimensional policy choice model with voter uncertainty. And last time we talked about expected utility, and we wrote down the maximization problem of the politician. Okay, so we wrote out the maximization problem, and then we said any optimal proposal strictly between the ideal point and the status quo would have to satisfy the first order condition, which I've just reproduced here. Okay, now this looks like a big mess, but let's try to get some insight from it. What I want to do is I'm going to keep this term by itself on one side. And I'm going to move all the other stuff to the other side. And I'll collect things a little bit because we have some common terms here. Okay, so when I move that to the other side, well, let me just take out the 1/2 as well. I'm going to have this utility from the status quo, P on that, minus this utility from the policy and this benefit of winning here, of getting the proposal passed. Keep in mind that that this expression here, because we're assuming that x is between the politician's ideal point and the status quo, the politician's utility is quadratic, and so evaluated at x, the slope of that or at x, the slope of that utility function is negative. So this is a negative number here. On the right-hand side, we have the utility of the status quo, which is pretty low, right? If you notice, it's down there somewhere, minus the utility from x plus whatever benefit of passing there is. So this is also going to be negative. It's easier to look at if I multiply both sides by -1, and that means over here I'm going to write the utility from x plus this benefit term minus the utility from the status quo. Okay, so why have I done this? Well, in this problem, as in a lot of choices that we face, at the root of the problem is a trade-off for the politician. Okay, so let's think about here. We have this optimal policy. What if the politician chose a policy closer to their ideal point? Well, obviously, if they get the policy passed, they're going to have a better policy. The problem is that that decreases the probability that they're actually going to get it passed. Okay. Similarly, if you increase if you increase x, the proposal, that's going to actually increase the probability that the proposal passes, but it's going to leave you with a policy that's not as good in that event. So what we have here with this first order condition is kind of a calculus expression of that trade-off. So on the one hand, if you move policy to the left, then the policy proposal will be better for the politician, and that's given by the -1 times this derivative. That's telling us the rate at which this policy is getting better, but that's going to be weighted or discounted by the probability that it actually passes. Okay. On the other hand, if you move policy to the right, your proposal will be more likely to pass, in which case, what is the gain then? Well, instead of the status quo, you get the policy from the proposal plus this extra bit from actually getting it passed. So the gain would be this difference here on the right. So that is multiplied by the density evaluated at this, the midpoint minus the structural ideal point. This is sort of measuring the likelihood that you actually change the voter's mind by pushing in a little bit, okay? And the first order condition is saying that those two things have to be balanced. So that's how calculus can be used to get some insight into this kind of decision problem and illustrate this kind of balancing of incentives. We could go into this more and put in a functional form for the density function. If it were uniform, for example, it would be pretty straightforward to solve this thing. But rather than do that, what I'd like to do is extend the model in a different direction by endogenizing the status quo. Okay, so remember in this model, if this is the policy space, we're assuming that the politician's over here and the status quo is somewhere to the right. Okay, so let's endogenize this. We've talked about endogenous status quos before, and the way we thought about it was we added a politician who made a prior proposal, right? So a first politician would propose something that then becomes like a status quo, right, for the second guy. And then we did this kind of, it's called backward induction, where for any possible status quo, we try to understand the optimal response of the second politician, and we kind of worked backwards from there. So what I want to do here is a little bit, it's quite a bit different. It's actually closer to the public good provision model, where we had two decision makers decide on activity levels simultaneously, so that neither decision maker could respond to the choice of the other. And in that model, we looked at the idea of a Nash equilibrium. So I want to pursue that in this policy choice model. So in particular, we're going to endogenize the status quo by adding a politician. So we're going to have two politicians. I'm just going to number them 1 and 2. And for each politician, they're going to have an ideal point. Okay, so let's say for politician I, their ideal point is PI. Where I ranges over 1 and 2. And we'll assume quadratic utility for both guys. So for person I, the utility from x is pi -1 times pi minus x squared. Okay, so now I have these two politicians, and I'm going to assume that each guy chooses a policy. Let's say XI is the policy choice of politician I, or policy proposal. And these are determined simultaneously. Okay. I'm going to again assume that there is a voter. Neither politician knows the location of the voter's ideal point. Okay. So we can think of the politician's ideal, or the voter's ideal point, as subject to this shock epsilon that's distributed according to some density F. And so basically, you know, we have the politicians choosing X1 and X2 simultaneously, and then the voter's ideal point is going to be realized, and they are just going to choose the better proposal, okay? So if politician 1's choice is X1 like this, and politician's 2 is X2 like this, we can understand this in the same way we did before. When will the voter accept politician 1's proposal? Well, we find this midpoint. Okay, and as long as the voter's ideal point is to the left of that midpoint, the voter accepts, or I should, squeezing this in a little bit too tight. The voter will choose X1. If the voter's ideal point is to the right of that midpoint, the voter chooses X2. Okay. So, so now instead of thinking about accepting or rejecting, you know, it's really a choice between two policy proposals for the voter. All right, so the probability that the voter accepts X1 then is going to have the same form as before. Sorry, minus the V naught. Now here I'm assuming this ordering X1 to the left of X2. But you can see that you know, there's a lot of similar structure to the model that we just did. So, so in this model, we're going to look for the Nash equilibrium. So just as in the public good provision model, a Nash equilibrium is going to be a pair. Now it's not activity levels, but policy proposals. X1, X2, and I'll put bars here just to distinguish them. So Nash equilibrium is a pair of policy proposals such that each politician is proposing optimally given the proposal of the other guy. So, so we write that as two separate conditions. First of all, politician 1 has to be choosing optimally. So their policy proposal X1 bar has to solve this maximization problem. They're going to choose X1 to maximize the expected utility given the equilibrium proposal of the other guy. Right? So that, what is the expected utility? Well, there's the event that the voter chooses X1, which has this probability here, in which case politician 1 gets the utility from their proposal plus whatever that extra is for just having your proposal accepted. And then there's the complementary event that the voter chooses X2 or 2's policy, in which case well, the probability of that is 1 minus this. And I forgot my V naught, which is going to disappear soon anyway, but I better put it in. Okay. All right, now, what's the probability that the voter chooses 2's proposal? Well, it's 1 minus that. In which case, politician 1 gets the utility from 2's proposal. Okay. All right, so first condition is politician 1 chooses their proposal optimally. The second condition is that politician 2 chooses optimally as well. So their proposal has to maximize their expected utility, which is going to have a similar form. There's the probability that the voter chooses their proposal. And now this is given politician 1's equilibrium proposal. And I keep forgetting the minus V naught. All right, so that's the probability that the voter chooses their proposal, so then they would get the utility from that plus the extra. And then with complementary probability, the voter would choose politician 1's proposal. In which case, politician 2 gets the utility from politician 1's proposal. Okay. All right, so it's the same idea as the public good provision model. It's a little bit more complicated here, just because we have this more complex expression for expected utility, but it's the same idea. So an equilibrium, it's a pair that solves this kind of interconnected system of maximization problems. The way we would solve that, at least the first order approach would be, we would calculate a first order condition for politician 1 and a first order condition for politician 2, and that would give us a system of 2 equations and 2 unknowns. Okay, that's just, you know, what we did in the public good provision model. So rather than get into the weeds right now, I think that we're going a little bit long. So what we'll do is I'll wrap this installment up, and I will continue this in the next one. I'll see you there.